seems to have maybe the light bulb's burnt out or something. I don't see any lights at all, so hopefully that'll get fixed in a few minutes. But we'll just deal with the one for now. So just decide. Before I started, I wanted to point out that the final exam has been set for this class, and what we're going to use that final exam period for is not a final exam, but for final project presentations. So I put on the course website, let's see, the date is Tuesday, December 13th, and our slot was 5:30 to 8:30 p.m., so I'm sorry that's so late. We'll probably just have food there, so make it a little bit more manageable for everybody to be there at that hour. But that's the date that we'll, and the time that we'll use for the kind of project presentations, and we're going to turn it into like a mini conference. So there'll be more details on that as the semester goes on, but do not leave Pittsburgh before then. Some people I know go places over Christmas or whatever, or holidays, but make sure you're here for that. And then the final project reports. So this is the presentation period. The final project reports I've set to be due 2 days after that. Okay, so that'll be Thursday, December 15th. So you have a couple of days to, revise or just incorporate any feedback from the presentations. Okay, any questions about that? It's kind of far away, but I wanted to mention it. Okay, and then we extended the deadline for homework 2 to be today, so it's due today at 5:30. I think that's right. But we couldn't push back the due date for homework 3, because then that would kind of have you doing homework right up until your little test. So homework 3 is still due the same original due date, which is not this Friday, but the next. Okay, so that was released over the weekend. Okay, so let's just go ahead and jump into duality in case unless there's any questions. Okay, so duality. We're going to start our unit on our second unit on kind of theory and optimality. And what we're going to cover is duality in linear programs, then duality in kind of general convex problems, then the KKT conditions, and then some connections between kind of duals and other aspects that you would have already seen in the course that you will see. So I personally like duality very much. This is one of my favorite topics. So I think it's very, very useful, and it's very beautiful too. So we're going to spend 2 lectures on it. Maybe I'm a bit biased. But linear programs especially maybe are very simple in the sense that we can think about duality kind of from a very hands-on perspective. So okay, just to remind you what we did last time, per our usual, we finished off last lecture our first order methods unit. So we finished with proximal gradient descent, which was this algorithm that allowed us to minimize the sum of 2 functions, both of which were convex, but only one of which was smooth. So that was this function g. And h was, non-smooth, but it was simple enough, in quotation marks, that we could derive its proximal operator. Okay, that's this thing I wrote down here. And we saw that proximal operators for like the L1 norm, for the nuclear norm, for other norms. Okay, thanks. For other norms or other functions, as on your homework, we can derive kind of closed form proximal operators, and this allows us to solve problems where the smooth part g is actually quite complicated, because the real kind of difficulty, so to speak, usually in these smooth plus non-smooth problems really just lies in evaluating this proximal operator. And then once we know how to do that, we just kind of pass in a usual gradient step as if we only had g to minimize, and then repeatedly call the prox. Okay, so that was proximal gradient descent. We saw that it was nice because it kind of encapsulated gradient descent when h was 0. Then we're just doing kind of gradient descent on g. It encapsulated projected gradient descent when h was the indicator function for a convex set. And it encapsulated a couple other special cases that we saw as being interesting. And the kind of last thing we did was that we proved that this has kind of the same convergence properties as gradient descent. And we could accelerate this to converge even faster at the optimal rate over all first order methods. Okay, so this was some of the best that is possible if all you're willing to assume is that the smooth part of your problem is is differentiable and has a Lipschitz gradient. Okay, so this is the best rate we've seen so far, too, in the class, on the order of 1 over the square root of epsilon. We're going to see, actually, okay, I kind of take that back. We saw a faster rate when we assumed strong convexity. Gradient descent converged at a faster rate under strong convexity. But even if you are willing to assume strong convexity, then acceleration provides you with an even faster rate than what we already saw. Okay, so it provides you with a better rate kind of no matter what level of assumption you're willing to make, whether your function is just differentiable or whether it's actually strongly convex. Okay, and when we return to second order methods, we'll see that actually all of these rates are actually quite slow in a sense compared to what second order methods can achieve. So now let's jump into duality for linear programs, a very kind of different topic. So we'll put on our theory hats for the next 4 lectures or so, although duality and optimality have really major implications in terms of the algorithms that we're going to use and that we're going to learn as well. So it's not just of theoretical interest. It's really a very, very important practical kind of aspect as well. But for the moment, let's just think about the following kind of somewhat abstract problem, which is that let's say I have a linear program, and I want to find a lower bound on the optimal value of my linear program. Okay, I want to find just a number, b, that has the property that b is less than or equal to the optimal criterion value, f star. And then we're going to kind of think about duality from just this very simple question. We're going to build up a notion of duality. So let's actually just do an example. Let's consider this LP. Okay, it's 2 variables, 2 scalar variables, x and y, and the criterion is x plus y. And I want to minimize that subject to the following constraints. X plus y is bigger than or equal to 2, and x and y are both non-negative. Okay, so what's the lower bound on the optimal value of this linear program? Well, that's really actually quite easy. It's just 2. Right? Because one of the constraints is that x plus y is bigger than or equal to 2. So no matter what I actually end up looking at the solution, right, whatever x and y end up looking at the solution, at least they have to be feasible. So they have to satisfy x plus y is bigger than or equal to 2. So that's definitely going to be a lower bound on the optimal value of the criterion, right? So that was almost vacuous. You guys kind of are looking at me like maybe this is a very silly example. Maybe we just got lucky, right? Because one of the constraints was actually equal to the criterion value in this case, right? X plus y was the same form as the criterion. So I'm going to try to convince you that we didn't get lucky for linear programs, and this actually is a strategy that we can kind of use in general. So let's try another one. Maybe I'll switch to the doc cam, but you guys can look at the slides for now, because I think it's actually easier if we just work them out. So you can take a look at the slides for kind of some higher level points, but let's just work on the doc cam for now. So let's try this problem. So I want to minimize over all x and y. The criterion now is x plus 3y, and I have the same constraints, subject to x plus y is bigger than or equal to 2, and x and y are both non-negative. Okay, what's an optimal value? What's a lower bound on the optimal value of the criterion for this LP? What would I do? So how would we get that, though? Let's work through that. So what would I do to get that?
Decomposing to x plus y plus 2y, which is greater than 2 plus 2y, and since y is greater than 0, that would be
right. That's exactly right. So let me rephrase that in a way that's actually just going to be maybe more helpful for what we're going to do that follows. So we can take this constraint and we can multiply it by 2, right? Because if y is bigger than or equal to 0, it's equivalent to 2y being bigger than or equal to 0. Okay, so we haven't changed anything. So we've just generated this constraint. It's still it's implied by these constraints, so it's still kind of perfectly fine to put this constraint in our linear program. And now let's generate another constraint, which is I'll take this constraint and I'll add it to this one. So if 2y is bigger than or equal to 0 and x plus y is bigger than or equal to 2, then that implies that x plus 3y is bigger than or equal to 2. Okay, so I've generated both of these constraints from my linear programming constraints. They both are always satisfied if we have x and y that are feasible. And look, this one is the criterion, x plus 3y. So the lower bound is then just 2 again. So that's a lower bound on our criterion. Okay, so that was may be very similar to what we did before. We just have to generate a few more constraints. Oh, perfect. Thank you. So let's try a more general example where I don't actually tell you somehow what the coefficients of x and y are. Okay, so p and q are constants here, but let's just suppose that we're going to keep them as arbitrary. So my criterion, let's suppose, is px plus qy, right, subject to the same constraints I think I had. Yeah, the same constraints. X plus y is bigger than or equal to 2, and y, and x is bigger than or equal to 0, and y is bigger than or equal to 0. Okay, the same constraints as before. So what would I do here? How would I, right, so how would I get a lower bound on the criterion here at optimality? So slightly, a bit of a departure from what we just did. But this is going to be a very similar strategy, which is that we're going to want to multiply these constraints, each by, let's say, positive variables, a, b, and c. Okay, so let's just do that. So each of these somehow is actually equivalent to the following constraint, right? ax plus ay is bigger than or equal to 2. This one is equivalent to bx is, this should say 2a. bx is bigger than or equal to 0, and cy is bigger than or equal to 0. So this is true as long as these are equivalent, as long as a and b and c are all non-negative. Right? Otherwise, I would have flipped the sign of these constraints. So I have to make sure that they're non-negative. But I've just generated a bunch of constraints, right? And now I can actually add all these together to get another constraint. So these constraints are all implied as long as I have x and y feasible, and so is this one. So I'll add all these together, and the coefficient on x is a plus b, right? And the coefficient on y is a plus c, and the right-hand side is just 2a. Okay, and now I'm going to say, well, if I happened to choose a plus b to be equal to p, and a plus c to be equal to q, then this thing would just be px plus qy bigger than or equal to 2a. So this is true. This is a valid constraint, right? As long as I actually choose a plus b equal to c to p, and a plus c equal to q. Okay, so if we could find any numbers a, b, and c that are all non-negative, such that a plus b is p and a plus c is q, then actually this constraint is implied by x and y being feasible. Px plus qy bigger than or equal to 2a, and so 2a is a lower bound. Okay, so in other words, b equals 2a is the lower bound, provided this is true. All this stuff that I wrote in that right-hand column. Provided that a, b, and c are non-negative, and a plus b is p, and a plus c is q. Okay? Let me pause for questions. This is kind of important that we all are on the same page for this. How do I make sure that p and q are non-negative? Well, I haven't. No, they're not non-negative, right? They're just necessarily. They're just constants that I said, right? So.
If p is negative, we can't make a plus b equal.
Correct. So that's actually a good point. We'll come back to that in a second.
Let's say it's a case where p and q are positive.
Uh-huh.
Our lower bound is 2a, so if you can make a as small as possible, that will give us the tightest. Actually, the wrong way. I was thinking you could just set a trivially to 0 and set b and c to be equal to p and q respectively, and then you would.
But we don't want. I mean.
We want the highest low.
Right. Yeah. They're both really good points. They're kind of foreshadowing what's to come. So we all agree this is a lower bound, right? For any a, b, and c that have these properties. And there's many a, b, and c that have these properties, right? If you, just pick a p and q and think about this as a linear system with positivity constraints, right? A, B, and C are non-negativity constraints. Okay, so what happens if we want the best lower bound possible? Okay, if we want the best lower bound possible, that means that we actually want to make 2a as large as possible. So notice what happens, something kind of neat, which is that actually we can find the best lower bound possible as another optimization problem, right? I want to maximize 2a, which is the lower bound I'm getting, subject to all these things on the right-hand side. But these are nothing more than just linear constraints, equality constraints on A, B, and C, and then linear inequality constraints. In fact, these are just quite simple. A, B, and C are all non-negative. So this actually, formulating the best lower bound possible, it's actually another linear program. And we call it the dual linear program to this original linear program, which we call the primal in the context of duality. So let's just kind of step back for a second. If you want to find the best lower bound on the optimal value of an LP, okay, with 2 variables and 3 constraints, then it turns out that actually doing so is another linear program, which we call its dual, and it has 3 variables. Okay, and you can notice by the way we constructed it, the number of variables in the dual is the number of constraints in the primal. That just came out of our construction, right? Because look, for every constraint in the primal, we defined an associated, what we'll call dual variable, which we use to multiply both sides of the constraint. So this guy was A, B, and C. We got 1 for each constraint in the primal. So there's this relationship that the number of dual variables is the number of primal constraints. And what we know is that for any A, B, and C that satisfy these conditions, which is called feasibility in the dual, so they're dual feasible, 2a is the lower bound. And therefore, if I maximize over all such things, I'll still get a lower bound on the primal optimal value. Okay, it'll still actually be that the maximum here is still a lower bound on f star. So let me pause and ask how many people think if I were to do this, I would get actually equality in the sense that the optimal value here will be equal to the optimal value here. Okay, and how many people think there might be a gap? So the optimal value here could be smaller than the optimal value here. Okay, I think that's good intuition. Pretty much everybody said that there's going to be inequality. And it turns out for linear programs, it's a fair kind of assumption. You pretty much always have that the optimal value of the dual is equal to the optimal value of the primal, except in very pathological cases, which we'll cover next time. We'll cover kind of when that happens next time. And now let me return to this other question. What happens if, let's say, one of P and Q are negative? Let's suppose P is negative. What is the optimal value going to be in the primal? So what's the optimal criterion value in the primal? Negative infinity, right. Because if, let's say, P was -1, and I can just drive x to infinity, it's feasible, and it makes the criterion go to negative infinity. What about the dual? What happens if P is negative? So if P is negative, then it's infeasible, right? I can't find A, B, and C that are positive to satisfy these constraints, or non-negative to satisfy these constraints. So our convention is, I think it's kind of typical mathematical convention, that the maximum over the empty set is also negative infinity, right? If I'm trying to maximize something over an infeasible set, I get negative infinity. So in that case, actually, we still do have this equality between the optimal value in the primal and the dual. Okay? So let's try another one. Let's try another one. So in this one, the difference is that I'm going to have an equality constraint in addition to inequality constraints. So here I think I said px plus qy subject to x being bigger than or equal to 0, y being less or equal to 1, and 3x plus y being equal to 2. Okay, so how would we derive the dual here? We'd actually follow very similar steps. We're going to introduce one dual variable per constraint. So here, I'll introduce the dual variable a. And my I can turn this constraint right into just ax being bigger than or equal to 0. Here I can introduce another dual variable, but I'm going to want to somehow put restrictions on my dual variables here, right? So here I have to have a being bigger than or equal to 0, right? Otherwise I couldn't write down these two as being equivalent. This constraint wouldn't follow from that one. Here I can introduce a dual variable, but then I'm going to have to actually restrict b to be less than or equal to 0, right? Because look, I have a less than or equal to sign here. And that's usually not kind of, it's just harder to do bookkeeping that way, to have variables that have some have positive signs, some negative signs. It's a very kind of trivial point, but it's easier if we actually write this as minus y is less than or equal to minus 1. Bigger than or equal to minus 1. Thanks. Yeah. Okay, so then I can think of this as minus by being bigger than or equal to minus b. Okay, and I'll say that my dual variable b has to be non-negative again. And here, I can multiply, let's say, both sides by a third dual variable. Let's call it c, and I get 3cx plus cy is equal to 2c. And what are my constraints on c? Nothing, because actually this is an equality. So whether c is positive or negative, right, or 0, this will always follow from that. So I don't need to somehow worry about any constraint on the third dual variable, c. Okay, now I just kind of play the same game as before, which is I add these three constraints. And I get that the coefficient on x is a plus 3c. And the coefficient on y is, it looks like, I think, c minus b, or minus b plus c. And the right-hand side is 0 minus b plus 2c. Okay, and if I'm able to make this guy equal to p and this guy equal to q, then this becomes px plus qy being equal to minus bigger than or equal to minus b plus 2c, and that will be the lower bound of my criterion, right, provided that, as we said, we have a plus 3c equals p and minus b plus c equals q. Okay, so there's our dual linear program. We want to make this lower bound as big as possible, so we want to maximize minus b plus 2c, subject to these constraints, okay, which I've written down here on the slide. Okay, so again, the number of dual variables is equal to the number of primal constraints. Right here I have three variables, here I had three constraints. The difference in this one is that actually one of our dual variables is unconstrained, because we had an equality constraint in the primal that it was generated from. Okay, so the rest of today, we're going to talk about duality and kind of general form linear programs. Then we're going to talk about an example. Actually, we have two examples today. But the first example I'm just going to kind of very briefly go through because we decided to make it kind of more, make a homework question on it. So that's the way you can kind of absorb the example rather than going through the lecture notes. And then I want to introduce a second take on duality. That's a very, very important change in perspective on duality. And then I'm going to finish with another example that we'll go through more carefully. So let's talk about duality for kind of a general form linear program. So departing from these examples, which are, I think, very helpful to see and work through, but trying to look at kind of LPs just in full generality. So so this is the form of the linear program we're going to look at. We're going to have our criterion being C transpose X, equality constraints AX equals B, and inequality constraints GX being less than or equal to H. Okay, and this of course, as we know, means kind of component-wise, right? Every component of GX is less than or equal to every component of H. So we may as well just kind of do it on paper one more time. It's kind of nice to see it worked out. Okay, so what we're going to do is we're going to introduce a vector of dual variables for all of these constraints and a vector of dual variables for all of these constraints. So let's call that we call it U for the equality constraints. Yeah, U and V. And we're going to require that V be non-negative in every component. And there's going to be no constraints on U, right? Because U is going to correspond to an equality constraint, so that it's perfectly fine for us to have this negative or positive components. So now notice that if I have any x that's feasible, right? If x is feasible, then that implies that I can take U transpose AX minus B, and I can add to it V transpose GX minus H, and that whole thing is going to be less than or equal to 0. Why? Because this thing is equal to 0 when x is feasible, right? So this term doesn't matter at all. It doesn't matter what U is at all. This term in every component is non-positive. Let's just call it negative, because I have trouble always saying the non-positive, non-negative stuff. So this is negative in every component. Okay? This is actually positive in every component. Right? So this thing is the inner product of, let's say, Vi with the ith component here, Gx minus Hi. But this thing is negative, and this thing is positive. So if I sum this up, right? If I take this inner product and sum this up, this whole thing is going to be negative. Okay, then just let's add back the possibility of equality. This whole thing is less than or equal to 0 if x is feasible. So it's a very simple construction, right? And I needed, of course, V to be positive in each component in order for this to be true. So now we just kind of do the similar arrangement that we had in the simple couple variable case, which is that we just try to make this look like the criterion. So let's just collect all the terms that are multiplying x. What we get is A transpose U plus G transpose V transpose x. So that is the these are all the constraints these are all the terms that involve x up here, and what's left over is minus B transpose U minus H transpose V less than or equal to 0. Okay, and so rearranged, if I want a lower bound on my criterion, rearranged, this is equivalent to saying that minus A transpose U minus G transpose V transpose x is bigger than or equal to minus B transpose U minus H transpose V. And provided that I can make this thing equal to C, if this was equal to C, right, then I would get C transpose x is bigger than or equal to minus B transpose U minus H transpose V. So this would be my lower bound. This is a constraint on my dual variables U and V. They must have the property that minus A transpose U minus G transpose V is C, otherwise I couldn't have formed this lower bound. And I must have V being non-negative. And other than that, there's no constraints on U, because it corresponds to an equality constraint. So by construction, right, if I have any pair of variables U and V that have that meet these constraints, and I were to form minus B transpose U minus H transpose V, that would lower bound the optimal value of my primal LP. And if I were to take the tightest lower bound possible, so I were to maximize over all U and V, it would still be a lower bound by construction, right? So we still get that the optimal value here is less than or equal to the optimal value here. Okay. How many people think that I have an equality at this level? So for a general linear program between the primal and dual optimal values. And let's just see if we can. Let me see if anybody can guess. So when would I not have an equality between these two? Because we already saw something, which was that, let's suppose the primal optimal value was minus infinity, which means that there's no finite optimal value. I can minimize this away to minus infinity, which we saw with this kind of simple example right here. If p was negative, then this was an example of a linear program whose optimal value is minus infinity. In that case, what do you think is going to happen in the dual if the prime optimal value is minus infinity? Most likely it's going to be infeasible, right? So if the dual is infeasible, then I'm going to get minus infinity here as well. Okay. How about if the primal were infeasible? What do you think is going to happen in the dual? So the primal is infeasible, then the minimum over this constraint set is going to be infinity, because the constraint set's empty. So again, our mathematical convention is to say that, if you're minimizing over an empty set, the answer is infinity. So what's going to happen in the dual?
No upper bound.
Right, there'll be no upper bound, kind of similar to this simple example where I can just maximize away to infinity. There's going to be some direction in the feasible set that'll just allow me to maximize the criterion indefinitely. That's usually what happens. So usually we always get strong duality in linear programs. Okay, that's typically what's going to happen, is that even if one of them is infeasible, the other one will be unbounded. So you'll still get strong duality. The criterions are going to match. The only time you're not going to get strong duality, I'll just kind of give away what we'll talk about next time, is when they're both infeasible. Okay, if they're both infeasible, then actually the optimal value of the primal is infinity, and the optimal value of the dual is negative infinity. That can happen. You can write down linear programs in which both the primal and the dual are infeasible. I just claim that they're kind of rare. They're pretty, they're not really ones you typically encounter. So this is a pretty nice example of duality in linear programs, but we're just going to go through it very quickly because there's a homework problem on this that does a really nice treatment of it. And there's also a really interesting paper that connects these two problems, max flow and min cut, from a historical perspective. So I would recommend you take a look at this paper. And I'm kind of not making this up when I say that the Russians, around the time of World War II, were thinking about solving max flow problems, and the Americans were thinking about solving min cut problems. And these are kind of the same thing. They're thinking about doing one in response to the other, but these are really kind of equivalent because of duality. And there's a very interesting history surrounding these problems. So let me just tell you what max flow is, and I'll tell you what min cut is, and then we'll just kind of state their equivalents and then leave the rest for the homework. So the max flow problem is, if you're given a graph, given a directed graph, then first we have to define a flow over the graph. And this graph, it has directed edges, but these edges also come with what are called capacities. So those are called Cij. If I have an edge between I and j, then Cij is the capacity of that edge. And think about it as like it's the maximum amount of things I can push through that edge. Okay, if this is like a channel, or this is a road, or this is a pipe or something, it can take no more than Cij if I were to try to push some amount of, some commodity across this edge. So those are constants. They just come with the graph. And what is a flow? A flow over the graph is basically a vector, let's call it f, that you assign to all the edges in the graph that has the following property. Each flow, so the flow across every edge has to be non-negative, which means you have to kind of be pushing things in the direction of that edge. You can't kind of be going against the direction given by that edge. And you can't push more through that edge than the capacity. So, here I'm thinking about assigning somehow some value that I'm going to be pushing between this edge from I to j that's bigger than or equal to 0 but less than or equal to Cij. And it has this other kind of really important balancing property, which is that the flow going into any node has to equal the flow leaving any node. Okay, so let me just pick some node k, for example. If I add up, suppose this is k, if I add up the flow going into node k, which means it's the flow from I to, let's say, I guess I call this j, but let's suppose this is just k. If I add up the flow from this edge, from this edge, from this edge, that has to equal the flow exiting k. Okay, the flow from k to all nodes that it's incident to. And that has to be true for all nodes in the graph except for two special nodes that we designate the source and the sink, which we're calling S and T. So the max flow problem is one in which you designate a source and a sink, and I want to think about pushing some commodity from the source to the sink, from S to T, via a flow. So I'm going to be pushing kind of stuff across all the edges. And it's, you can think about, I want to maximize, let's say, the flow leaving S. Because of this balancing property, that's going to be the total value of the flow, subject to my vector f actually being a flow. Okay, so satisfying these properties. That's the max flow problem. Okay, so you can think about how to distribute kind of some commodity across this graph if I'm going to want to be pushing it from source to sink. And we can derive the dual of this. This is just a linear program, right? All these constraints are just linear constraints on our variable f, and this is a linear criterion. And what we were doing before is deriving duals of problems that were minimization problems, right? And we're getting lower bounds on the dual. Well, it's completely equivalent to deriving an upper bound for a maximization problem, right? If I just had put a minus sign here, I could have thought of this as a maximization problem, and I would have gone through the same steps and derived an upper bound via the dual. And that's what is more relevant here, because our original LP is a max, not a min problem. So I'm not going to go through the steps because you'll do that in your homework. And actually, I think it's probably easier to do this with the second version of duality that we'll learn in a second, in just a moment. But this is what you end up with. Okay, you end up with another linear program, and it's a minimization problem. Okay, just like when we started with a minimization problem, we got a maximization problem. Now we start with a maximization problem, and we end up with a minimization problem. And interestingly, this problem is the linear program relaxation of what's called the min-cut problem. So min-cut is another kind of well-studied problem over graphs, and we have the same setup. Let's suppose we have the same setup. We have directed edges, we have capacities on the edges, and now the min-cut problem says that I want to divide my nodes into two groups. Okay, so here I've just highlighted one of the groups. Okay, and the other group is just the complement of that, such that the sum of capacities of edges crossing the cut is as small as possible. Right? So remember, every one of these edges has a capacity attached to it. And I want to divide my, let's say I want to divide my nodes into two groups such that actually, if I look at the edges crossing the cut, which means that there's one of the nodes is in one group and the other node is in the other group, that the sum of the corresponding capacities, so in this case, this capacity and this capacity and this capacity, that's made as small as possible over all kind of configurations of nodes into two groups. That's the min-cut problem. So that's actually not a linear program. That's an integer program, because we're thinking about kind of assigning variables, nodes, just to be in one group or another. So we actually have kind of binary variables in our optimization problem, which is written down here, and which we'll go through kind of carefully on the homework. It turns out that the dual, okay, of the max flow problem is just the LP relaxation of that integer program. So it takes those binary variables, and it just allows them to be anything between 0 and 1, rather than having to be equal to 0 or 1. And by construction, what we know is that the value of the max flow is less than or equal to the value of its dual. Because we by construction, right, the dual here is going to have, is an upper bound the criterion in the primal. That's where this first inequality comes from. And because that is the relaxation of a minimization problem, that's an integer programming problem, that's actually going to be less than or equal to the capacity of the min-cut, right? Because this isn't what we know about kind of relaxing, say, a problem into a convex one, right? If I'm trying to minimize something over a constraint set, if I convexify the constraint set, if I make it larger, the minimum can only get smaller. That's why I have this less than or equal to here. So we've established kind of this sequence of inequalities from everything we know so far in the class. And what's a very interesting result called the max flow min-cut theorem, which I think is due to Ford and Fulkerson in the 50s, is that actually these two are the same. The capacity of the min-cut and the value of the max flow are equal. Okay, it's a pretty, I think, interesting result. And it says that actually we have equalities for everything here. And the min-cut and max flow problems are equivalent in that sense. Okay? And you'll go through that kind of more carefully on the homework. But this is just another example of where we saw something called strong duality, which means that the primal and the dual have exactly the same optimal value. Right? That's kind of implied by the fact that I told you that this guy, the value of the max flow and the capacity of the min-cut, are equal. So in particular, just for the perspective of our current lecture, this means that this dual problem didn't have a gap between its criterion value and the primal problem. We had an equality there. Question?
Yeah, so what would be the runtime complexity if we want to solve this problem in this formulation?
For the max flow or min-cut problem?
Yeah.
They're fairly cheap. I'm sure that there's state-of-the-art that's beyond what I kind of remember, but I think like basic max flow problems run close to linear in the number of edges. There's a bunch of kind of specialized algorithms you can run for max flow problems where they don't treat them as generic linear programs. So I think some classic algorithms textbook would probably kind of give a thorough treatment of that. But I think that some of them run close to linear in the number of edges. So yeah, they can be solved at large scale. Other questions? Okay. So let's take another perspective on linear programming duality. And this one is going to be actually really quite helpful for what we see going forward. So let's go back to this problem. And let's do what we did before, which is assign a dual variable for this set of equality constraints and a dual variable for this set of inequality constraints. And let's constrain, just as we did before, the dual variable corresponding to the inequality constraints to be non-negative. But let's think about kind of a somewhat different construction for lower bounding the primal criterion value at optimum. So let's start with the criterion. And let's just say that for x feasible, this is going to be bigger than or equal to the criterion plus a bunch of stuff. In particular, I'm going to add u transpose ax minus b, and I'm also going to add v transpose gx minus h. Okay, why is this the case? That's because for x feasible, this is going to be equal to 0. When x is feasible, this is going to be component-wise less than or equal to 0. And this is component-wise bigger than or equal to 0. Right? So this whole thing is going to be less than or equal to 0 when x is feasible. Right? It's really the same argument we made actually up here to begin with. It's the very same thing as this argument. When x is feasible, if I take u transpose the primal equality constraint plus v transpose the primal inequality constraint, this whole thing is less than or equal to 0. Just applying that again, but in a slightly different way. So I'm saying that if I take the primal criterion value and I add to it all that stuff, right, it could only have gone down. C transpose x plus all this stuff. Okay? So that means that if we were to minimize, let's suppose we denote by C the set of primal constraints. So this is the feasible set. So let's just start off by saying that, well, if I were to look at the minimum over all x in the set C, all feasible x, C transpose x, so that's clearly equal to the primal criterion value f star, right? Just by definition. But now for every feasible x, I actually know that I can lower bound the primal criterion by the primal criterion plus this term. Okay, this is what I get by taking my dual variables and multiplying them by my primal constraints, adding all those up. That's bigger than or equal to the minimum over all x that is feasible of C transpose x plus all that stuff. U transpose AX minus B plus V transpose GX minus H. Okay, and this in turn is bigger than or equal to what happens if I minimize over all x, this modified criterion. because minimizing this function of x, over the set C, which is just feasible points, can only give me something that's larger than minimizing this function of x over all x. Right? By removing the constraint that x had to be feasible in this minimization, I can only make its optimal value lower. And this thing, this is actually just a function of u and v. And we define it, usually denote it by GUV. Just a function of u and v. So before we even kind of look at this more carefully, what we've already established is that suppose we could just write this as a function of u and v, which it really is, but suppose we could write it analytically as a function of u and v. Get rid of x completely. We've established that this function, GUV, lower bounds the optimal criterion value as long as v is non-negative. Okay, so what we've just established is that we've shown that f star is bigger than or equal to GUV, provided that v is non-negative. Right, that was what we showed in this argument. Which means that if we wanted to get the biggest lower bound possible, our dual problem would be to make this as large as possible, right? We maximize over all u and v this function GUV, subject to v being bigger than or equal to 0. That would be another dual. Okay, another way to derive a dual, right? Because we've established a lower bound on the primal criterion value for all u and v such that v is positive, and now we've made that lower bound as tight as possible. So this, the optimal value here is still going to be less than or equal to f star. Right, the optimal value of this problem, which we usually call g star, we have by construction that the optimal value in this problem, g star, is less than or equal to f star. Okay, another way to derive a dual here. So let's go through and let's actually figure out what this function g is. So what is g for our linear program? So GUV, right, is defined as the minimum over all x of this guy, C transpose x plus U transpose AX minus B plus V transpose GX minus H. Okay, that was the definition of G. And it's helpful just to rearrange this so that we just get terms involving x. So, I mean, we just look at all the terms that involve x kind of grouped into one. So let's just do that. This is, we get C plus A transpose U plus G transpose V transpose X minus B transpose U minus H transpose V. Right, I just grouped all the terms. Now we can ask ourselves, what is this? So this is a linear function, right? This is a linear function of x. Think about that of the form, you know, like A transpose x plus something. What is the minimum of that function over all x? It's negative infinity unless the coefficient that multiplies x, right, this vector that whose inner product we're taking with x is 0. So this is actually going to be equal to minus infinity if C plus A transpose U plus G transpose V is not 0. Because if that wasn't 0, then this is a linear function. I could make it as small as I want, right? I could just take it, I could take x in some direction to make this whole thing equal to minus infinity. Trying to minimize it, right? And if C plus A transpose U plus G transpose V is 0, then what's the optimal value here? What's the minimum? Just right. It's just this term, minus B transpose U minus H transpose V. So that's our function, right? Two cases. If we happen to be looking at a U and V for which C is not equal to, let's say, minus A transpose U minus G transpose V, then our function G is minus infinity. And if we happen to be looking at a U and V for which C is equal to, let's say, minus A transpose U minus G transpose V, then our function G is just a linear function, just minus B transpose U minus H transpose V. Therefore, this is kind of the key, maximizing over all U and V such that V is non-negative, maximizing this guy is equivalent to maximizing over all U and V minus B transpose U minus H transpose V, subject to the constraint that C must be equal to minus A transpose U minus G transpose V, and V must be bigger than or equal to 0. Because if that constraint didn't hold, then our function G would be minus infinity. So it would never achieve the max, right? We'd never achieve the max without U and V. So this is exactly like what we do when we take indicators and put them into constraints. That's really all I'm doing here, okay? Just taking this, which gives us minus infinity in the maximization problem, and making it a constraint. So this is the dual problem. And what do you notice about it? It's exactly the same as what we had before. Okay, so this second perspective on duality gave us exactly the same linear program as what we had from before. Okay, the reason why this construction is so helpful is that think about what happens if we had a general problem. So I'm just going to foreshadow a little bit for what happens next time. What happens if I had, let's say, a problem of this form? Okay, what are our two strategies? Our first strategy is to multiply these by constraints. Multiply these by dual variables. Enforce that the dual variable corresponding to this constraint has to be bigger than or equal to 0. And then our first strategy would say, I'm going to try to take a linear combination, right, of this and this, taking a linear combination of this thing. I'm trying to somehow make this equal to f of x. Right? If I could make this equal to something involving f of x, then I could rearrange this to get a lower bound on the primal criterion value. That's what our first strategy in the linear programs were doing, right? So strategy number 1, which tries to get this looking like f of x plus something less than or equal to 0 is not going to work in general. Because if f wasn't a linear function, how could we get f out of just a linear function? So that works for linear programs. It doesn't work the moment f is not linear. And that's kind of the remarkable thing about the second strategy, which is that it's always going to work for us, no matter what f is. Second strategy is always going to work for us. So it's going to work for any f, provided that f is convex, let's say. Well, even when f is not convex, it still works in some sense. So this one is not going to work unless f of x is linear. But strategy number 2 will work in some sense for any function f, and in a more precise sense for convex functions. Okay, so that's why we kind of think of the second strategy as being so useful. And just to kind of step through at a very high level what we did one more time, we just took the primal criterion and we formed something called the Lagrangian. Then took the primal criterion, we added the inner product of our dual variables with our constraints. And then we thought about, instead of minimizing this over just the feasible set, we actually thought about minimizing this over all x. And that was going to give us the lower bound. So form the Lagrangian, which means takes the primal criterion, multiply dual variables by constraints, add that to the criterion, that's called the Lagrangian, and then minimize the Lagrangian over all x. And that always gives us a lower bound on the primal criterion value. Okay, let's take maybe a short break, and then I'll come back and do one more example. So this is, I think, a pretty interesting example about what's called a mixed strategy for playing a very basic game in game theory, a matrix game. And you can read more about it online. I'm sure there's a pretty rich history of this example as well. And there's also a bit in the Boyd and Vandenberg textbook on this. And here's the setup. So let's suppose we have 2 players. And here I have Javier, who's co-instructor for the class, and myself. And we're going to be playing a game against each other. And the game's going to involve a payout matrix, P. And the way it works is as follows. So let's say Javier chooses one of m options, 1 through m. And let's suppose he chooses option I. And I also choose, let's say, one of n options. Suppose I choose option j. Then we go to that entry of the payout matrix, okay, Pij. And Javier is going to pay me that amount, Pij. And you don't have to feel bad for him because this can actually be negative. So this payout matrix has both positive and negative entries. And if it's negative, it means that I'm actually going to be giving him money. So that's the setup. Okay, so we're each going to be kind of choosing from a list of options. And what's going to happen is we're going to have to, respect this payout matrix after those are chosen. And instead of choosing options deterministically, we're going to each put down what's called a mixed strategy in the context of this example. But it's just a probability distribution over these options. So for example, Javier is going to choose a probability distribution that I'm going to call x. And it has m entries, and xi is going to be the probability that he chooses option I. And I'll also specify a probability distribution, let's call it y. And yj is going to be the probability that I choose option j. So after specifying those, then let's say we just generate an option according to these distributions. It's no longer deterministic. So the real kind of crux of the game is in specifying these distributions x or y. Okay? And you can imagine some distributions obviously being better than others in terms of the payouts. So the expected payout, right? If I want to ask what's the expected payout from Javier to me, and again, this could be positive or negative because these entries could be positive or negative. So it's not, this game is not set up in a one-sided way. It's just that we have to talk about kind of one direction. That's it. It's the sum over all options, right? I and j times the payout for that option times the probabilities that I would have chosen, let's say j, and Javier would have chosen I. So this is the expected payout over that strategy. Sum over all I and j, xi yj times pij. And we can write that more succinctly as just x transpose that matrix P times y. So this is the kind of important bilinear form. So it's linear in x with y fixed, and it's linear in y with x fixed. So that's why I'm calling it bilinear. This linear bilinear form, right? X transpose py tells us the expected payout for any given pair of strategies x and y. So let's consider kind of 2 situations. We're going to see a very interesting kind of conclusion arise, which is that it doesn't really kind of matter, in some sense, who we try to skew the game in favor of. So let's just consider both situations. So let's suppose because Javier is older and wiser, I can admit that, he's going to allow me to know his strategy ahead of time. he's actually going to tell me X. And he's going to say, go ahead, this is my strategy. Go ahead and design Y based off of X. So and what I would do then is I would just look at the expected payout, X transpose PY, and I'd say, well, X was given to me. I'm going to choose Y to make this as big as possible. I want the most money possible coming my way. But my Y has to be a probability distribution, right? I can't just choose, arbitrary vectors Y. I have to actually choose a probability distribution. And so I want to maximize X transpose PY over all vectors Y that have non-negative components. So I have to have some non-negative probability of choosing every option. It could be 0, but it can't be negative. And they have to sum to 1, right? That's just saying that the vector Y has to kind of specify a probability distribution over all the options. And if you look at this maximization problem, well, the answer is going to be just to choose the value of Y that corresponds, just to choose Y to be all zeros and then 1 in the entry that corresponds to the largest value of P transpose X, right? This is just because X transpose P times Y, I can just write that as P transpose X transpose Y, right, which is the sum of P transpose X I yi. And if I'm only allowed to choose probability distributions, then what I'm going to do is just look at the value of X, value of I for which this is largest, P transpose X, and put all my mass there. So I'll just take yi to be 1 for that option and 0 everywhere else. That's the best thing to do. Okay, and that means that the maximum, right, overall Y of X transpose PY, for which Y is in the simplex, is just the maximum component of P transpose X, for that reasoning I just explained. Okay, so Javier, remember, is wise. So he gave me his probability distribution, but he knows that once he gave me X, I'm going to do this for Y. He's a very wise man. He knows that as soon as he gives me X, I'm just going to put all my mass on the biggest entry of P transpose X. So he actually is going to give me a very special X, not just any X. He's going to give me the X that makes this the smallest, because he wants to pay me the least money possible, right? When he gives me X, he knows I'm going to act kind of optimally and put all my mass on P transpose X in the biggest component. So he's going to give me an X that makes that actually the smallest to begin with. So his payout coming to me is as small as possible, which means that he's going to choose a distribution according to the following optimization problem. Minimize over all X, right, the payout that he would be giving me if I were to act optimally for that X, and that is the maximum of all components of P transpose X. And again, his X has to also be a probability distribution, so he just can't choose any X. He still has to look at X's that are non-negative and that sum to 1. Okay? So this would be his distribution if he were to reveal his distribution to me and know that I were to act optimally. And then in response, he would kind of choose the distribution that had him paying the least amount of money to me. Any questions about that? Yeah.
Too relevant, but is that last problem, is that of a form we've seen thus far, like a convex?
Yeah, it's perfectly relevant. So let's let me just bounce that back. Is this a convex problem? So who thinks this is a convex problem and can explain it to me? Yeah. True, but without kind of going through that, so why is this convex? We can say it's convex immediately from what we know about maximum of convex functions, right? Each of these guys is just actually, think about it like taking EI transpose P transpose X, where EI is the vector with all zeros but a 1 in the ith spot. And that's just a linear function of X. I'm taking a maximum of convex functions. It's convex. Convex constraints. So it's just a convex problem. Yeah?
No, just the info why the first player chooses. So that's the solution.
Why is that the case? So it's because the payout, right, coming to, it's actually the second player, coming to me in this case, from Javier to me, is the expected payout is x transpose py, right? So what we derived up there. And we can just write that as the sum of p transpose x in the ith component times yi. And now think about having yi having, let's say, positive components and summing up to 1. And let's suppose that the biggest entry of p transpose x was the first entry. Suppose you put like probability 0.9 on the first entry, and then you distributed the rest of the probability throughout the rest of the components of y. Well, that would be suboptimal, because I could just kind of move that right to the first entry and just get strictly more, because this is the first entry was the biggest. So if I have to be choosing the probability distribution that kind of makes this expected payout the largest possible, all I do is, in case the first entry is largest, let's say, I just take yi to be 1, and I just put zeros everywhere else. Otherwise, I just get some, right? So, for example, if p transpose x1 is largest, then I just take yi to be 1, and I take zeros everywhere else. So the payout just ends up being p transpose x in the first component. So then just in general, it just depends on what's largest, right? The payout is just the maximum entry of p transpose x. Okay, all good questions. So let's flip the script. Let's suppose somehow we were in, some alternate universe where I was actually the wiser one, and I said that I'm going to allow Javier to know my strategy beforehand. I'm going to give him y. Okay, and he has to choose his distribution x in the way that's best for him possible. Then he's going to want to choose, right, x. Let's just rewrite this now in a slightly different way. He's going to want to choose x so that this expected payout is smallest, because he doesn't want to have to pay me much money, right? And actually, since it could be negative, by making it as small as possible, he might even be receiving money, right, if the smallest expected payout was negative. So he wants to choose x to minimize, right, x transpose py over all x that are non-negative and sum to 1, which for the same reasoning that we just kind of used up here is going to be equal to the minimum over all j of py. So whenever I give him y, this is how he responds. This is he responds by choosing basically x to put all the mass on py in the biggest entry, and then this is what he would be having to pay to me. Okay, and then because I'm wise or greedy or both, I'm going to choose y to make this as big as possible, right? Because I know that when I give it to him, he's going to act in the optimal way, and I want to eventually kind of get as much coming to me as I can. So I'm going to choose y to make this as big as possible, right? Because the payouts are coming to me. So I want to choose y to maximize the minimum of py in the jth component over all j, subject to y being a probability distribution. Okay, so that's kind of the best possible payout I could hope for in the situation where I gave him my strategy beforehand. And this is the payout that I would see if he gave me his strategy beforehand. Okay, this has both players acting kind of optimally. So let's call this f1 star. It's the optimal value of that program. And let's call this f2 star. It's the optimal value of this program. Then, well, we clearly know that f1 star is larger or equal to f2 star, right? Because in a situation in which I know Javier's strategy, right, it has to be more favorable to me in terms of the payout I'm going to get than the situation in which he knows my strategy. Right, if I look at some other payout in a situation in which I knew his strategy ahead of time, it has to be more favorable than one in which I gave him my strategy ahead of time. That's saying that the payout going from Javier to me, it's only going to be larger in the first scenario. f1 star is going to be bigger than or equal to f2 star. That's, some of you could maybe just argue based on intuition about what's happening here, right? But a big surprise is that, and this is called von Neumann's minimax theorem, is actually that they're equal. So it doesn't matter. It doesn't matter who has the upper hand in terms of knowing the other person's strategy. If both players act optimally, which we've kind of used in driving these problems, then the payout's going to be the same in either scenario. It's going to be exactly the same amount of money going from Javier to Ryan. So that's, I think, pretty surprising when you think about it in a kind of game theoretic context. But it was a very important result and spawned a lot of kind of research and development. And this is one we can actually prove. Or at least we can formulate both problems as linear programs and show that they're duals. Okay, and then by the time I show you that they're duals, well, we kind of already said that strong duality almost always holds in linear programs. Right? So the optimal value of the dual and the primal should be pretty much the same. So that's what's going to happen here. So let's just spend the last 5 minutes formulating these as LPs. So that first problem, right, this first problem was to minimize over all x P transpose x the maximum over all I, subject to x being non-negative and summing to 1. So as was kind of hinted at earlier, this first problem is actually we can transform it into a linear program. So I'm going to introduce a variable, let's call it t, and I'm not sure what happened in the slides. I meant to say there meant to be a t here. Sorry, missing the criterion. This is equivalent to minimizing over all x and t, subject to x being bigger than or equal to 0, 1 transpose x being equal to 1, and p transpose x being less than or equal to t. Now you can see that these two problems are equivalent because at the solution I'm going to take t basically to be as close as possible to the entries of p transpose x because I want to minimize this, right? And that's just going to set t to be equal to the biggest entry of p transpose x, which is what the criterion is here. Okay, so this is a way to reformulate this problem. And this is an LP. This is an LP because my variables x and t, and everything here is linear in x and t. Okay, so let's use the second strategy for driving the dual because that's going to be the one that we're going to somehow want to get comfortable with for kind of from now on for general programs. Although it would be fine to also use the first strategy since this is a linear program. And what we do is we take the criterion and we add to it basically Lagrange multipliers corresponding to the constraints. So the dual variables multiplied by the constraints. So I'll just kind of do it on the fly here. So u is my dual variable corresponding to this inequality constraint, but I'm going to flip this around to be minus x being less than or equal to 0 because I want to constrain all my dual variables to be positive when I need to. And that'll give me minus u transpose x. And then I'll have, what did I call it? I think I called it v for the equality constraint, 1 minus 1 transpose x. And then I called it, I think, y for this last constraint. So this is y transpose p transpose x minus t times, I just put a 1s vector here, so it's clear that this is a vector. Right? That's t in each component, p times the 1s vector. And then I want to minimize this over all x. Okay, so if I were to collect the terms that involve x, right, I'll see that, sorry, I want to minimize this over all t and over all x, over my primal variables. Right, so if I were to collect the terms that involve x first, I get minus u minus v times the 1s vector, and I get plus p transpose py. Right, and all the terms that involve t, I just get 1 minus y transpose 1 times t. And what's left over looks like just v. Is that right? Okay, so if I were to minimize this over all x and t, you can see as I've written on the slide, I would get minus infinity if these two things were both not 0. Okay? But if they're both 0, I just get v. That's the dual function. So now the goal is to maximize this over all configurations of dual variables where u has to be non-negative, and so does y. And when we do that, you see that these are going to appear as constraints in the dual problem. So the dual problem is after we eliminate u, because u kind of plays an unnecessary role as a slack variable, is just the following. Maximize over all now y and v, the criterion which you saw before, which is just v, right, that comes from this, subject to these constraints plus a non-negativity constraint on u, which after we eliminate them becomes just y being bigger than or equal to 0, 1 transpose y being equal to 1, and py being bigger than or equal to v. Looking at this is exactly the second problem, right? This is just a way of kind of rewriting the second problem as a linear program. Because I'm going to make v kind of as close to the entries of py as possible in order to maximize this, which means I'm going to be getting the minimum over all entries of py as the criterion, right? It's just exactly this problem. So what we've done is we've shown that the first problem, this guy, is actually a linear program whose dual is this guy. And I think I said it already. Linear programs, we always have strong duality unless both problems are infeasible, unless both problems do not have any feasible points. And we'll kind of assert that next time when we talk about duality. But look at these programs. They're clearly feasible, right? This feasible set is just the simplex. So take 0. 0 is in the simplex. So that's all we need. They're both feasible, which means that the optimal values are equal, which is, I think, quite a surprising result in this context. OK, that was it. Make sure to turn in your homework if you haven't already today, and I will see you guys on Wednesday.